Let's go over our inventory practice problems. Okay, so go ahead and read through it real fast, and then here's the important information we're going to need to know. We have 9,600 tires expected to sell next year. Annual carrying costs are $16 per tire, and each order placed costs $75. So our annual demand, which is D, is going to equal 9,600. Our order cost is going to be S, and that's $75. And then our annual holding cost is H, also called our carrying cost, is $16. That one's per tire. Now, first we want to find our economic order quantity. And this is going to be the order quantity that's going to minimize our total holding. And again, that's the same thing as carrying cost and our annual ordering cost. So what we're going to do is going to have Q equals the square root of 2D S H. And so when we go ahead and plug things in, that's going to give us 2 times D, which is 9,600, times 75 all over 16. That's a square root, by the way. And that's going to give us square root of about 90,000, which equals just about 300 tires. So I'm going to go ahead and erase this to make room for our next step, which is going to be finding our total cost. I'm going to leave our 300 tires because we're going to need that for the next piece. So to find our total cost, it's going to be our annual holding cost. I'm writing it like this. That's not exactly how it's written. That's just to keep it simpler. And then our annual ordering cost. This is going to be annual holding cost is quantity divided by 2 times H. And then our annual ordering cost is going to be our demand over quantity times S. I'm going to change it to red. So over here, our quantity is 300. H is 16. We'll do one at a time. So this is going to come out to 300 divided by 2 is 150 times 16. So our annual holding cost comes out to roughly $2,400. And then our annual ordering cost is going to be our demand, which is 9,600. Quantity we just found is 300. And then S is going to be 75. So 9,600 divided by 300 times 75, and that's going to also happen to give us 2,400. I think it's just a coincidence that they're the same. It's not always going to be the exact same number. And then we add those together to get 4,800. So our economic order quantity is going to be 300 tires. That's the best quantity they're going to want to order so that they can minimize those costs. And then our total cost is going to be $4,800. Okay, let's move on to number 2. So here they are using 4,000 toggle switches a year. We have our price breakdown. It costs about $18 to prepare an order and receive it. Carrying costs are 18%. I'm going to write that here because I think seeing a percent is easier than the word. And we're going to do the same thing. It's going to be a little different because of the numbers we were given, though. So we need to determine the economic order quantity and the associated total cost. So first off, our demand is going to be 4,000 a year. Our order cost, S, is going to be $18. And then our inventory carrying percentage is 18% of the unit price. So we're going to say that's I. Now, we first need to find our economic order quantity. So Q equals 2 ds all over H. However, this is going to be a little different because we don't have H. To find H, we're going to go ahead and do I times P. We found I, that's going to be 18% times P. In this case, we're going to start with 82 cents. And the reasoning for that is because we're going to say if they order 1,000 or more, it's going to be 82 cents each. We're trying to get the best possible price, and we know they order 4,000, so we know that's at least over that 1,000, so that's how we're going to try and calculate and see if we can get the best price there. So this is 82 cents, sorry, 0.82. So when we plug that in, we're going to get 0.1476 for H. So now we can go ahead and plug things in. It's going to give us 2 times 4,000 times 18 all over 0.1476. That's a square root, by the way. And that's going to give us a quantity of roughly 987.73. Now, we need to check the feasibility for these ones because of how the prices are. Now, we said if we ordered over 1,000, it's 82 cents. This quantity is not over 1,000, so we can't really use this as we move forward. So when we come to find the total cost, we're going to do things a little differently. So I'll show you that when we get there. So that means we have to move on to the next piece. I have this written down, so that will come back later. Okay, so now we need to try again. Let's try it with our 85 cents each. Same, we order 500 to 999. So we're going to do the same thing to find H. 85 cents times 18%, and that's going to equal 0.153. So now we can go ahead and plug things in. 2 times 4,000 times 18 all over 0.153. And that's going to give us sorry, I have my notes on the side. Anyway, so that's going to give us 970.14. Now this is feasible because this is in the range of 500 to 999. So now we can go ahead and move forward. Because this works, we don't need to try the next level being the 90 cents because that just means it's going to be more expensive. So now we need to see which is best for the associated total cost. And that means we were going to want the lowest total cost. Now, this one's a little odd because the first one we found, remember how that first one was 987.73? But we couldn't use that number because you need to order 1,000. So we need to make sure that when we're doing the total cost, at least for that first one, because it's not 1,000 or more, we have to set it to at least 1,000 for us to get that discount. I'm going to go ahead and erase this just to make some room again. And our total cost is going to be calculated slightly different for this one. Our total cost is going to be our annual holding cost plus our annual order cost plus annual purchase. So we know that this is Q 2 times H, D over Q times S, and then this is going to be D times P. The P that we found is going to be these numbers right here, the 82 cents and then that 85 cents when we get there. So first, we're going to do the first one. Remember, like I said, we can't use the 987 for this first one. We have to say it's at least 1,000 that they're ordering. And then our H that we found before is going to be 0.1476 plus 4,000 all over 1,000 times 18 plus 4,000 times our 82 cents. That's going to give us 73.80 plus 72 plus 3,280. I'm going to erase everything here real fast. And I'm going to just go ahead and put this number off to the side because we're going to need to do it again for the next one. And this first option is going to be 3,425.80. Let's do blue for the next one to tell them apart. So this next one, we can use the 970.14 we found. And this is going to be the 85 cents one. So we're going to divide that by 2 times H is 0.53. Plus 4,000 all over 970.14 times 18 plus 4,000 times 0.85 cents. I'm running out of room here. And that's going to give us 74.22 plus 74.22 plus 3,400. That's going to give us, for our second option, is 3,548.44. So in this case, it actually is going to be better to do our first option of ordering 1,000 units because that's going to be less expensive. All right, this is number 3. Okay, so we have 1,000 cans of tomatoes a month, 40 per day for each of the 25 days. Usage can be approximately by a normal distribution with a standard deviation of 3 cans per day. Lead time is constant, and then we have our carrying cost and order cost. So D, I'll write them up here. D, if it lets me. There we go. D is going to be 1,000. Now remember here, there's going to be a daily one. So capital D is 1,000. That's going to be our monthly. And then lowercase d is going to be 40 cans per day. Lowercase d is our daily. And then we have our order cost. Oops, that's an S. And that's $2 per. We have our holding cost. Again, we're going to make this capital because it's per month. And that's going to be 0.02. And then our lead time is going to be 4. Our standard deviation is going to be, why can't I write? There we go. Our standard deviation is going to be 3 a day. And I thought we were, and then we're given Z that we're going to need to find that later. Okay, so first off, we're going to find our economic order quantity. We've done this one before. This one's not too bad, so we're going to go ahead and plug that in. Q equals the square root of 2 times Z times S all over H. We already have these, so it's going to be 2 times 1,000 times 2 all over 0.02. It's the square root, and that's going to give us approximately 447.21. Now we do want to remember we want to round this because again they're going to be whole numbers. They're cans of tomatoes. We can't have 0.21 of a can of tomatoes. So we're going to get 447. Now we're going to see how many cans of tomatoes they should have on hand when he orders. This is our reorder report. We're finding out when to order, and we're using the formula for when demand varies. We have a lead time that is fixed, and we need it to cover our expected demand plus our necessary safe stock. So first we're going to go ahead and find our demand during our lead time, which is D times LT. We have our D, which is 40, and our lead time, which is 4, and that's going to give us 160 cans expected. And then we're going to find our safe stock, and that's going to be Z times our standard deviation of LT. Now, in order to find this, it's going to be our standard deviation times the square root of LT. So that's going to be 3 is our standard deviation. The square root of LT, our LT is 4, and that's going to give us 3 times 2 equals 6. So now what we can go ahead and do, I'm going to erase this real fast, just so there's some more room. Okay, so now what we can go ahead and do is plug things in for our SS, which is going to be Z times the square root of LT. So Z was given, it's 2.33. We just found this to be 6, and that's going to give us 13.98 cans. And then we're going to go ahead and find our reorder point, which is our expected demand plus our safety stock. So our expected demand is going to be that 160 we found earlier plus our safety stock we just found, and that's going to give us a total of 173.98. Once again, we are going to want to round this to ensure our 99% service level. This is so that demand does not exceed our supply, so we're going to round that to 174 cans. And then just remember, this 160 came from that demand during our lead time that we found earlier. They're gardening outside. I hope that's not too loud. Anyways, okay, we have a mean of 150 bottles per day, standard deviation, a mean of 6 days, standard deviation of 1 day for delivery time, and then how many should they have on hand in order to be 90% sure of not running out before delivery arrives, and how much safety stock should be carried. And we are given our Z. So our mean daily is going to be D with a line over it, lowercase, again because it's daily, that's why we're doing a lowercase, is 150. Our standard deviation for our daily is going to be 10, that was given right here. Our mean LT is going to be 6, and then our standard deviation of LT is going to be 1. So then we can go ahead and find our expected demand. So that's going to be the mean of our demand times our mean of LT, our lead time, and that's going to be 150 times 6, and that's going to give us 900 bottles. So now we're going to go ahead and find our safety stocks. The safety stock is going to be when both our demand and our LT vary formula. That's why it's a little different. If we went ahead and looked at the slides he gave us, they're going to be a little different depending on what we have. So this involves calculating the standard deviation of lead time demand. And that the standard deviation of lead time demand is going to be look like this. So the overall formula, let me erase this to make room again. Our overall formula for our safety stock is going to be Z times LT. Oops, that's our standard deviation. Sorry, that looked odd. Plus this times. Now, if you're like me, I initially looked at this and was like, wow, there's so many numbers, but it's actually not too bad. We just need to plug things in. We know what LT is, that's 6. And then we know what this is, our standard deviation is 10. This 2 is just we're raising it to the second power. That's all that is. It threw me off at first, but it's not that bad. Oops, I don't know. Oops. Okay, sorry, we're multiplying these, and then we're going to go ahead and again, we are plugging these in. D is going to be 150 raised to the second power times our standard deviation of lead time, which is 1 to the second power. When we do all that math, this is all under a square root. So once we do that, we're going to get the square root of 23,000, and that's going to come out to our standard deviation of our standard deviation of lead time demand, is 152 bottles. So now that we found that, we can plug that in and make this formula seem a lot simpler. So now it's just going to be equals Z times our standard deviation of lead time demand, and that's just going to be 128 times that 152 we found, and that's going to give us approximately 194.56. We want this held in excess so we don't run out. Again, we're going to round that to be 195. And then for our reorder point is going to be the excess demand plus our safety stock. The first one's going to be that 900 bottles we found before, plus that 194.56 we found, and that's going to give us 1,094.56. Again, we want to round this because we can't have a portion of these root beers, or beer, sorry. We want 1,095 on hand when our reorder is placed, again, because we don't want to round out. Hopefully that all makes sense.